Welcome. The title of today's notes worksheet is Inverse Functions. Similar to composition of functions, inverse functions represent a topic that you explored in Algebra 2. Hopefully we'll be able to revisit some of those ideas here and maybe expand on it a little bit. It should be noted that we will take a look at the notion of inverses when we deal with exponential functions and logarithmic functions. So we will see the idea come up again. And also those going on to Pre-Calc 2, you will also sort of revisit the idea of inverses within the context of trigonometric functions. So let's get some good foundation going here with the concept behind it, and then also just formalize maybe some of the algebra as well. So here we go. At the top of your page, it should say something like one-to-one function, if you want to kind of box that up here. Just one tie-in with inverses first, the idea of a one-to-one function. So let me read the definition, and then we'll play it out with the couple examples that I see on your page here. So for each x in the domain, there is exactly one y in the range. And as it says on your paper, of course, this is the definition of a function. Each x produces one y. No doubt about that. Now the secondary piece, and if you don't mind there, let's just go ahead and underline the and no y in the range is the output of more than one x in the domain. And as it says, this was what would make it one-to-one. Now at this stage, that probably just looks like a whole bunch of verbal jargon, and that's fine. Let's see if we can solidify that idea, though, with the example 1 and example 2 that you see on your sheet. So, kind of an Algebra 1 question and an Algebra 2 question to get us thinking about it. So if I gave you just a graph on the coordinate plane, how could you quickly just determine if that graph represents a function? And if you remember way back when from Algebra 1, we would just apply something nice and simple, what is called the vertical line test. And I won't describe the vertical line test. I think that's old news at this stage. So we have that. Just, is the graph a function? Throw the vertical line test. If it passes, yes. If it doesn't pass, no. Now we're going to take a look at a secondary piece. So after it passes the vertical line test, could we then determine if the graph of the function is also one-to-one? So maybe based on my inflection, you can kind of figure it out. Vertical line test just to see if it's a function, and then the additional piece, of course, would be the horizontal line test. Okay, and it works the same way as you probably saw in Algebra 2. So what I have on your paper for example 2 to really put it together is two functions. And by the way, this one just happens to be y equals x squared. This one right over here just happens to be y equals x cubed. So two easy ones to kind of take a look at. Both are functions. Let's be clear on that. They both pass the vertical line test. I hope you're clear with that piece. So what I would ask you is, which is which? Which function is one-to-one, and which function is not one-to-one? Okay, so if you see it, I guess the argument can be made that this right over here is the one-to-one function. Because if I go ahead and draw a horizontal line anywhere at all, it will only pass the graph at exactly 1 point. At most 1 point, I should say. All right, so that would be the case right there. So that one is one-to-one. Each x produces only one y, and each y comes from only one x. That would be the situation at hand. The best way to really view that definition from above is to see what doesn't make it one-to-one. So I kind of gave it away, but this one is not one-to-one. And I'm hoping you see that it does not pass that horizontal line test right here. I'm going to go ahead and draw one right there. And as you can see, it touches here, it touches here. It simply does not pass that test. Now let's dive a little deeper if that's all right with you. I mean, we've got this graph. I know this graph pretty well. This point right here, of course, is just going to be 2, 4, right? This point right over here is negative 2, 4. So here's the idea, I guess. It is a function. Each x produces only one y. But in this case, if you notice, this y value comes from two different x's. It comes from the 2. It also comes from negative 2. And so it does not satisfy the second part of that definition. It's not one-to-one. Okay, so I hope that makes somewhat of a difference or a clarification piece in terms of that definition. So this y comes from more than 1x, so it's not 1 to 1. Each y here only comes from 1x. It's 1 to 1. All right, nice. Let's move on to my next board here. And what we're going to do is take a look at two different perspectives on inverses today. A more informal approach, a more conceptual approach, if you would, and then a more formal or more algebraic approach, probably on the back side. So I think we put this sentence, or you saw this sentence before on a previous notes worksheet, and I think I probably had mentioned it's one of the most important sentences of the entire semester. It really breaks down the notion of a function. A function is very simply a set of rules telling us what to do to the input. An input goes into a function, the function manipulates it, out comes an output. The analogy I'm going to use here today, everybody, is it's like wrapping a gift. And bear with me on this if you don't mind, but the premise would be this. In terms of wrapping a gift, you take a gift, you put it in the box, you put wrapping paper on the box, you put tape on the wrapping paper, and then you put the bow on top at the end. So think of that analogy in creating creating a function. So now guys, the next sentence. An inverse function, and by the way, box stat notation, you've seen it before. That doesn't read f raised to the negative first. What that reads is f inverse, or the inverse of f. So let's be clear on that notation piece right there. So an inverse function of f very simply undoes whatever f does. So if creating a function is like wrapping a gift, then very simply creating the inverse is like unwrapping that gift. Again, keep that in mind. I think you'll sort of enjoy going through this conceptually, and it hopefully will click in terms of what it represents. Okay, so let's go ahead and start this out here with an example and get us thinking about those two pieces. So let's go ahead and do letter A. I think we've kind of done this before verbally. What does the function tell us to do? If I was to give you any input, what would you do? What does the function tell us to do to that input in order to create the output? So the way I'm seeing this, of course, is the first thing I would do is square the input. So if you don't mind, can you write that piece on your paper? We would square the input, whatever it may be. And then the second piece, the second rule, so to speak, would be to subtract 1. So after squaring, we subtract 1. Okay, so we're going to use that premise in order to go ahead and then create the inverse. So we are going to undo those rules right there. So I'm just trying to find a good spot for it. I'm going to do it all the way out here and then come on back over here. So here's the idea. Just put a little 1 in place and give me just a moment. But let's go back to the analogy. So creating a function is like wrapping a gift. I do this, then I do this. Well, creating the inverse is basically undoing those steps or unwrapping the gift. Now, if you remember my description, everybody, when you wrap a gift, you put the present in the box, you put the paper on top of the box, you put the tape on top of the paper, then you put the bow on last. When you unwrap the gift, everybody, what do you start with? The bow. And so if I do this and then this, well, to undo that, I start at the bottom and I work my way back up. Here's the bow. Start with the bow and work your way backwards. So I guess I would ask you this. How am I going to undo subtracting 1? And of course, you would add 1. So start with the bow. That'll be the little mantra to repeat as we just do it informally. So what I do is I have my input right here, and I start with my input, and I'm going to undo those steps from above. The first thing I undo is subtracting 1 by adding 1. Great. Now again, I work backwards, and in this case, I'm going to undo the square. Actually, I'm going to write that because I want to come back to an idea that you've seen before with this phrasing. But basically what that means is square root, right? Okay, so I take what I have now. So I've took my input first, I added 1. This is what I have. And now I take that and I square root. Now notice the phrasing, no? Just one thing to note, of course, when you undo a square, and this will hopefully allow you to not forget it when you see it in the future, what are you always supposed to take when you undo a square? Both roots, plus and minus. So that's, in reality, what you've just created, of course, by undoing these steps in the opposite order, kind of working backwards, you've created the inverse of f of x. Sorry, that didn't get written in very well there, but I hope you see the notation. So the inverse of f of x. Beautiful. All right, good. Now let's move on, everyone. C and D. If you don't mind, tie them together, because whatever we answer for C probably will be the same for D. So first and foremost, is f a one-to-one function? Let's go back to that beginning. Can you envision the graph of x squared minus 1? By the way, which is, of course, just a parabola. Is that going to pass the horizontal line test? Absolutely not. If it doesn't pass the horizontal line test, it's not one-to-one. So now, everyone, what I'm going to do is graph the function and its inverse. And what I want to know is, independently, is the inverse a function? So it is time to bring the calculator up. We're going to draw several conclusions from this. And I've got some stuff in there, so let's clear that out. And let's go for it. So everyone, if you would, x squared minus 1. Let's just do zoom, number 6. And of course, does that pass the horizontal line test? No, certainly not. Let's go on back. And here's where it gets a little interesting. I need to go ahead and type in the inverse, but I have both roots, right? I have the positive root of x plus 1, and I also have the negative root of x plus 1. And I do have to type them in independently into the y2 and y3. So positive root and negative root of x plus 1. Everyone see that piece? Okay, very good. I'm actually going to go ahead and hit zoom again. I don't know if it'll make a dramatic difference or not, but I'm going to use that square window that comes up on occasion, kind of see it a little better, I think, make all the tick marks the same. Again, it's not that big of a deal. Okay, so ignore the original function for just a second. Ignore that and focus on this piece right here. So that is the entire inverse in all its glory. By the way, here is the positive of the root, and here is the negative of the root. If I was to just give this to you on a coordinate plane and ask you if that's a function, what would you say? You would probably say no, because if you notice, that does not pass the vertical line test. And that's the connection that we're going to be having here. In fact, that's going to be our first conclusion. If this doesn't pass the horizontal, this doesn't pass the vertical. And so I said C and D go together, and here we go. Graph the function and its inverse. Is the inverse a function? Absolutely not. Good. And that's the connection. So let's go ahead and start our conclusions. As you can see, yikes, there are 4 of them, but that's number 1. So here's what I would have. If the function is one-to-one, so that's kind of why I started the lesson this way. So if the function is one-to-one, then the inverse is a function independently. By the way, we're going to see exactly this piece. We'll come back to this idea when we do exponential functions and logarithmic functions. We're going to see that relationship form. And this conclusion actually goes into that piece. And obviously, the other way we would say it is if the function is not one-to-one, then the inverse is not a function. So there's number 1 in place. All right, now number 2, and 2, and 3, and 4, well, all of these really go together nicely. So there's a little reflection piece. We've kind of seen some reflections before. Not sure if you remember this one from Algebra 2, but go down to the y4 if that's all right with you. And we're going to type in a nice little diagonal line in here. How about just y equals x? So this would be the line on the coordinate plane where all of the x's and y coordinates are the same. And as you are going to see when I hit graph, it's actually the reflection line to the graph of the function and its inverse. So if you can picture it, do your best here. But if you can fold this graph over this line, reflect it over, it should land directly on top of this over here. These kind of moves down here. This would kind of move over here if I folded this over our y equals x line. And the reason that occurs is actually more along the lines of numbers 3 and 4. I probably won't go into it in a ton of detail, but if you're curious as to why this is the case and you'd like to ask, please don't hesitate. I'll go over it independently with you. But let's get this conclusion in. So the reflection line. The graphs of a function and its inverse are reflected over the line y equals x. And as I said, that's the line where all of the x's and y coordinates are the same. All right, very nice. Now, number 3, I'm going to use the calculator to sort of get this going. So I'm going to perform one of our little functions on the calculator. So we have this. Hope everyone's comfortable with that piece. If you get a chance, how about hit second and then trace for me? And let's go to value. That's a good one to do right here. I'm going to hit value, and I'm just going to type in a random x. Really, it's not going to have any rhyme or reason to it. I'm going to just do x equals 3. And so I have 3 comma 8. Does everyone see that right here? So there is a point, out of the infinite number of points, by the way, there is a point on the graph of the function. Now that actually goes somewhere to the graph of the inverse. And so this has a corresponding point on the inverse, and the question, of course, is where? So keep this ordered pair in mind, 3 comma 8. Now I'm going to go on back, hit second trace, and I'm going to go to value again. And in this case, everybody, I'm actually going to hit 8. And when I hit 8, nothing really pops up that's going to blow your mind, because this 863 is actually still on the function. But I want to get it on the inverse, everyone. So what I'm going to do is just hit the down arrow for a moment. And I hit the down arrow, and notice now it puts me on part of the function. And look at the ordered pair. There's 8, negative 3. So 3 comma 8 was right up here. The corresponding point on the inverse is 8 comma 3. Now I could do that for the infinite number of points on the graph of the function. If I switch the ordered pair, what that does is it puts me on the graph of the inverse. And that is conclusion number 3. So let's get this in place, which leads greatly into number 4. So if xy is a point on the graph of the function, then, very simply, y comma x is a point on the graph of its inverse. Awesome. All right, good. So by definition, what happens is an inverse is going to be created by taking all of the x's and y's and switching them. And that's what makes our inverse. Good, which leads into number 4. Some quantities that you've looked a lot at over the last couple years and will continue to do so is domain and range. So let's see if we can formulate one more conclusion and then kind of relate it to what we see up here. So first and foremost, the domain of the function, and think about that for just a second now. What I want to know is what's that now equivalent to? So think about that. That would represent the input of the function, all of the inputs, all of the x's of that function. Well, where did all of those values go in the inverse? They were the inputs to the function. Now, as you can see, they become the outputs. They're the second part of the ordered pair on the inverse. So all of these values move to the output of the inverse. They become the range of the inverse. So domain of the function is actually now equal to the range of the inverse. Wonderful. And this we haven't been able to do up to this stage, or at least when I asked you to find the range of the function, we just did it graphically. We didn't now do it algebraically, but we should be able to now pull off the range of a function without using a graphing calculator. Because what do we know about the range of the function? All of those values, all of those outputs right there become the what? They become the inputs of the inverse. And if they become the inputs of the inverse, they make up the domain of the inverse. And we can solve for the domain algebraically. So once we know this, then we know this piece right here. Wonderful. Okay, now I could do a little domain and range on this piece. And I think I might just take a moment on that if it's all right with you before moving on. If you don't want to write this piece down, that's totally fine. But here's what I'm going to do just below just to reemphasize this last point right here. So I'm just going to do this. If you want to watch for literally just 60 seconds, that would be great before we get into the next piece. So domain and range. So you ready for this? In this case, I think we had, what did we have there? F of x equals x squared minus 1. Now the domain of every quadratic is all real numbers. No doubt about that. Which means, actually, right away, I can start thinking about the range of the inverse. So this was the plus or minus root x plus 1. Here's what we have over here. So as our conclusion told us, the domain of our function should be the same as the range of the inverse. Those two are the same, and we'll look graphically in just a second. Now this we weren't able to do without a graphing calculator, but let's see if we can wait and just confirm it. Look at our function right here, guys. It's a square root function, isn't it, when all said and done? And what do I know about the square root function? I know that whatever is underneath that square root can't be negative. Has to be greater than or equal to 0. And so as a result, you see that those x values really have to be bigger than or equivalent to negative 1. That would be the domain of our inverse. Which means, again, all of those values sink in right over here. And so without even graphing this quadratic right over here, I know that its range has to be bigger than or equivalent to negative 1. And that's how it looks. Watch. Let's just do a quick view on it and move on. Hey, here's the function. Definitely horizontally. It's going left and right forever and ever and ever. Domains all reals. And look at the range, everyone. Vertically, it's just from negative 1 up. So vertically, here's a low point at negative 1, up. How about now domain of the inverse? Look at this. As we move left and right on the graph, it looks like as we move left, there's an end point right here at negative 1. And it's only to the right of negative 1. And so there it is right there. And the range, all reals. Going up forever and ever and ever, down forever and ever and ever. It's a winner. So kind of cool. Some good conclusions to be drawn there. And again, those going on to Pre-Calc 2, all of these will come back. We will revisit those in a trig context. Let's get to the next board here. So example 4, and then we'll formalize this up and do just kind of the last 3 pieces. So example 4, just keep it nice and simple. I have a function represented by 4 ordered pairs. So inputs and outputs. This produces that, et cetera, et cetera. Inputs produce outputs. If I want to create the inverse, so in this case, I don't know how to draw a bracket, so I just do a squiggly, but something like that. Our inverse will be made up of 4 ordered pairs as well, because our function was made up of 4 ordered pairs. And very simply, how is a function created? By switching all of the x's and y's. The inputs become the outputs become the inputs. So instead of negative 1 comma 5, hey guys, 5 negative 1 is part of the inverse. Instead of 1 comma 2, it's 2 comma 1. 5 comma 3, and 5 comma 8. Oops, sorry, last one. I had a brain freeze there for just a sec as I was thinking of something else. So 5 comma 3, and there we go, 8 comma 5. Phew, caught myself. Wonderful. Okay, one thing before we move on, and we've answered the question. There's the inverse, no two ways about it. Here's what I would ask you just very, very quickly. See if you've been paying attention to this. Is this function one-to-one? It is a function. Each x only produces one y. This produces that, that produces that, that produces that, that produces that. Each x only produces one y. Is it one-to-one? No. If you notice, the 5 comes from 2 different x's. So it's not one-to-one. So use the conclusions, guys, just trying to emphasize a couple things here. If the function is not one-to-one, is the inverse a function independently? Is this a function over here, guys? No. So this inverse, even though it is the inverse of our original function, it is not a function independently. And why is it not a function independently? Because of those 5s, because the 5s now move to the inputs. Does a function work like this? Can a 5 produce the -1 and the 3 simultaneously? No. Each input produces only one output. It can't produce 2 of them. Okay, hope that works. I'll go ahead and just draw that piece again. That's the problem. Okay, let's formalize this up and get into just the last 3 problems. So the conclusion that we took some time to develop, but I think it does pay off in the long run here, is how to find an inverse. And so very simply, an inverse is created by interchanging the roles of x and y. That's how an inverse works. X and y switch. So interchange the roles of x and y. The y's become the x's become the y's. That's pretty much it. So that's what we're going to go ahead and do through these last problems here. I've got some strategies to do that, and we'll pull it off. So let's read what's on your paper here, and let's see if I can clarify a couple notational pieces. But we're going to use this premise. So if a function is defined by y equals f of x, then the inverse is defined as, here, let me keep it simple. It was y equals f of x. Look at that. There's your inverse. That's pretty much it in a nutshell. And so the problem is, well, it's good. We have our inverse, right? Switch x and y, you've created your inverse. But in your experience dealing with equations in 2 variables, have we ever really looked at it as x in terms of y? No. It's always been y in terms of x. And so what that is this next sentence right here. We're going to get what is called the explicit form of our function. And that means we're going to go ahead and solve for y. So bear with me. I'm going to formalize this notation up just a touch for a moment. And if it scares you, don't worry about it, because I will kind of break it on down right here in our strategies. But basically, it would work like this. This is your inverse, but it's in the wrong form. So what I'm going to do is actually solve for y and see what that's equivalent to. So here's the premise, guys. I need to get y by itself. So I have to undo the f composed of y. Well, this is why it's usually taught after the idea of a composition, because what I'm going to do is compose it of its opposite. So what I'm going to do is this piece right here. And anything I do to the the right-hand side, I also have to do to the left-hand side. So I'm going to compose x of the inverse of f. Okay? So this is not multiplication. This is basically a composition, so to speak. F is composed of y. Now what I'm going to do is compose the inverse of f of y. Well, just use your instinct here, everybody. What happens to these 2 pieces? And go back to the wrapping a gift and unwrapping a gift and idea. So what is the relationship between a function and its inverse? Well, an inverse very simply just undoes whatever f does. So if f tells us to do something here, this is just going to undo it. And when it undoes whatever f told us to do, I'm left with what I start with. In this case, just y. These undo each other, and you're left with this. Good. And then this piece right here, there we have it. And so the bottom line here is, again, don't get too tied into this piece. But the bottom line is, when I switch x and y, I've created the inverse. And what this does now is when I solve for y, I've elaborated on the fact that solving for y is the true inverse of f of x, as you can see. Okay, so create the inverse by switching x and y, and when you solve for y, you see that is equivalent to the inverse of f of x. All right, well, let's get moving. So it says strategies for finding the inverse of a function. As I wrote above, interchange x and y. The only problem is it's in the wrong form. It's what's called the implicit form. And again, that's just not very user-friendly, especially when we get to exponentials and logarithmics. We're going to have to work with that. So at this stage, what we do, very simply, is we solve for y. And when we do, when we solve for y, it changes it from implicit form to explicit form. And that's the form that we work with algebraically. And when we solve for y, as we saw, that is the inverse of f of x. Okay, well, it's time to just do 3. The way I played it out here, everyone, for examples 5, 6, and 7, it's sort of easy, medium, hard. So forget the wrapping a gift and unwrapping a gift. I think it's brilliant conceptually, but it's time to just formalize it up and let our algebra skills take over. And that's what I'm going to do for this last set. So number 5, determine the inverse and domains and ranges. Yeah, let's put it all together. So box, let's do it. And is everyone comfortable with the fact when you see f of x equals x cubed plus 1, this is really y equals x cubed plus 1? Okay. Well, if I'm going to create the inverse, watch this. It's the easiest step probably all semester. Here's the inverse. Switch x and y. Instead of y equals x cubed plus 1, it's x equals y cubed plus 1. How easy is that? All right, now all I have to do, because this is not a form that I work with consistently, I want to just solve for y. So how would you solve for y here? How would you get it by itself? Well, guys, we subtract the 1 on both sides. So I've got that. How do I go ahead and remove the cube? Cube root. Now, unlike a square, a cube root is what is called 1-to-1, meaning the cube root of a positive is positive, the cube root of a negative is negative, only one answer for each cube root. So we don't do a plus or minus, long story short there. And we get, when we solve for y, we get this, cube root of x minus 1. Now, again, you created your inverse, and you solved for y. You got it in the proper form. What does this y equals represent? Well, at this stage, what we then determined with that notation up here, this is now equivalent to the inverse of f of x. And so I would substitute, if you would, as well. That would be great, really to solidify that piece. When you solve for y, you've established the fact that that is the inverse of our function. Function, inverse. Wonderful. Now, just real quick on this piece. If you did the whole wrapping a gift and unwrapping a gift on this one, it does work out nicely. This one's simple enough where you would get exactly this piece right over here. But I like it better formally, to be honest. Okay, let's get domains and ranges. So domain, look at the function here. Think of numbers you can put in place of x. Can I cube any number? Yeah. And then add 1? Certainly. Domain is all reals. Put that in, you know you can do it. Which means, by the way, what is the range of the inverse? Without even thinking, without even looking at that inverse, I know that the range is all real numbers. Okay, very good. Now this is the piece that we've always been missing. So we come over here and we say, all right, well, what is the domain of the inverse? Cube roots work differently than square roots. And I think I had already mentioned, can I take the cube root of a positive number? Sure. Can I take the cube root of 0? Yes. Can I take the cube root of a negative? Yes, I can take the cube root of a negative. Is there any restriction on taking a cube root? No, there's not a restriction around. So what happens here is the domain of our inverse is all reals, which means, without even graphing this guy right up here, I know its range was all reals. Let's go ahead and look at this one. This one is a great one visually and puts all of the little conclusions in place. So you ready for this? Okay, so I have x cubed, and what was that, plus 1. And then I go into the math menu, math, there it is, number 4. So cube root x minus 1. Very nice. And let's go ahead and hit graph. There it is. Look at that. Domains and ranges, by the way, work perfectly. Look at the range on that one. Definitely all reals. Oh, it looks absolutely awesome. I'm going to go ahead and do one more piece. How about we throw the y equals x in? This one we should really be able to see it. How does that look for a reflection line? The graph of the function, the graph of the inverse. Cool. One last thing just to tie the connections. Those conclusions that we drew before, let's go value on this. Again, I'm just making stuff up here. How about when x is 2? There it is. There's 2 comma 9. Ready? Let's track that point. Where's the corresponding point? Let's hit 9. Nope, that's not what I wanted. There it is. Now it's on the inverse. Here was 2, 9. Here's 9, 2. And we did that for the infinite number of points on the function. Change them. They're on now the inverse. Cool. All right, 2 more. As I said, it goes easy, medium, and then hard. So first order of business, everyone, I'll follow the exact same procedure. I won't graph it. I think we've kind of proven our point with the graphs. So let's go for it, everyone. First and foremost, the easiest step around, just switch x and y. There is the inverse. Let's get it in a better form. So how am I going to fix this, by the way? I do have an issue. What I'm trying to solve for is stuck in the denominator of a fraction. So, and again, I'll do this formally, but basically all you're going to do is cross multiply or kind of bring that up there. But basically I'm going to multiply both sides by y plus 2. I hope everyone's in agreement that that's probably the best course of action. These would cancel and I get 4, and then I get y plus 2 times x. Okay, good. Now, at least what I'm trying to solve for is no longer stuck in the denominator. Now, let's see if we can get rid of the stuff, the extra flack, and get this y by itself. So I see this y plus 2 times x. Are you okay undoing the multiplication of x by dividing by x? There we go, divide by x. And then once I divide by x, seems like it's pretty clear cut. I have to get the y by itself. What do you say we throw a minus 2 on the back end there? And so 4 over x minus 2. You could probably go a little further, and if you'd like to, you're more than welcome to. I don't see a real need, though. That's as good of an inverse as any. And so again, when you solve for y, what you've really done is you have found the inverse of our function. So let's notate that. And there it is. Okay. Hey, it would be great to pause the video for a moment and come up with some domains and ranges. See if you can go 4 for 4. Here's what I have. So I looked at the function, of course, rational family, and I do know I can't divide by 0, so I have to exclude negative 2 here. No doubt about that. And again, I'm just trying to draw tie-ins here, so that means right away that has to be the case. Even without graphing this, I know that you'll never get a y value of negative 2. Now the inverse, let's go up here. I can work with domains because I can figure out what's going on with x. In this case, of course, I know 4 divided by x. Well, that can't be 0. I can't do 4 divided by 0, so that would be the case right here. And then as a result, I know that I would exclude 0 from the range of the function. So if I graph this, probably getting infinitely close to 0 from both directions, but it's never going to hit. Nice. One more. Hard one. Same run through. Hard function. Same family, by the way, rational. Let's see if we can get the algebra. Again, I would love for you to work a step or two ahead of me. So first of all, keep it easy. Switch x and y. And notice the issue at hand here. Yikes. So I have 2 y's in the equation. I have to solve for y. Unfortunately, I have 2 of them. So that's going to have to be fixed. And one of them is in the denominator of this fraction. So 2 issues to deal with. So what do you say we deal with the first one here? You okay multiplying both sides by y plus 1, or really just bringing that, I'm sorry, the y minus 1, just bringing that up? So I have the 2y plus 1. Now I will tell you, I will get this going for you. Unlike the last one, it definitely helps here to distribute. So I'm going to go ahead and draw the arrows in for you. And so you get xy minus x. All right, very good. Now here's, I guess, what I would ask. Where would you go from here? And remember your goal, and maybe you'd have a fighting chance at this. You have to solve for y. You have to get a y equals on one side of the equation and nothing but x's on the other side. So what would you do? Well, if you have to solve for y in terms of x, wouldn't it benefit us to get the y's kind of all collected on the same side of the equals? So what I'm thinking is, right now you've got them on opposite sides. That doesn't help. That doesn't allow me to get a y equals. So let's go ahead and bring this over here. And this is just kind of in the way. Let's bring that. Let's add x to both sides and bring that over here. Let's just kind of change the positions. And so as a result, I have this piece. It's not ideal, of course, because I still have two different y terms, but at least now I'm focused on the fact that I can get a y equals. All right, now how do I go down from two y terms to eventually writing just a single y? And you know this skill. You've been working on this skill now for years. How do I do it? Well, it all comes down to the idea of factoring. By factoring out that y, and now you see definitely why I moved that x to the other side. When I can factor out that greatest common factor of y, I only write a single y on this side of the equation, right? Perfect. So now I have y times x minus 2, and that should look somewhat similar to example 6, because now all I have to do is undo the multiplication of x minus 2 by dividing it. So I am seeing that right there. Have I solved for the y in terms of x? Yes. Is it in explicit form? Yes. Is it the inverse of our function? You betcha. Let's put it in. So x plus 1, x minus 2, boxing it up, happy as can be. All right, there's your inverse. Look at those algebraic steps. I think there's some good ones there. I don't think they would necessarily go intuitively, so just watch how that algebra plays out, but very nice. All right, go get me some domains and ranges, if you would. Here is what I'm looking at. Domain of the function can't be 1. Can't divide by 0. 1 has to be excluded, which means I come right over here. Y value can't be 1. Now I focus on my inverse a little bit, and I look at that inverse, rational family. X can't be 2. And so what does that mean right over here? Without even graphing this, I know you will never see a y value of 2. Nice. All right, so that wraps up the inverses there. Some really good math. And as I said, this sets the foundation for when we see families of functions and inverses together, specifically this semester, exponential functions and logarithmic functions. So we will be revisiting this algebra here when we see those two pieces. And then also those going on to Pre-Calc 2, one of the trickier things to deal with in Pre-Calc 2 is inverses with the trigonometric functions. So we will have to play that out. Hey, of course, thank you for listening, and never hesitate with any questions.